In this video, we're going to see tunnel diode, which is also known as Isaki diode, which is named after its inventor Leo Isaki, who invented it in 1957. This diode works on a phenomenon called tunneling. That's why it is called as tunnel diode as well. Let me take two crystals of same semiconductor material, where one is doped with trivalent impurities so that it becomes p-type, and the other doped with pentavalent impurities so that it becomes n-type. Its energy band diagrams would look like this, except that the Fermi energy level is not shown here. For tunnel diodes, the doping that we do would be really very high. So on p side, if I take heavily doped, let's say this is p plus, instead we can actually call it p plus plus because it is heavily doped. And when doping is increased, the Fermi energy level would move very close to EV compared to EC. But in this case, it is heavily doped. The semiconductor itself becomes degenerate, and as a result, Fermi energy level not just moves close to EV, instead it goes into the valence band. So I'm representing the Fermi energy level of the p side of the tunnel diode. Here, let's call this EFP, Fermi energy level on p side. And similarly on n side, when we heavily dope it, the Fermi energy level wouldn't just move close to EC, instead it goes into the conduction band itself. Then the semiconductor is degenerate semiconductor. So I'm representing Fermi energy level here, EFN. Hypothetically, if we join these two materials to make a tunnel diode, then there are a lot of electrons on n side which would move onto the p side, and a lot of holes on p side which would move onto the n side. As a result, the electron energy of p side material would increase, and electron energy on n side material would decrease. As a result, when the tunnel diode reaches equilibrium, the Fermi energy level would be constant throughout the p-n junction diode because there won't be any net current flowing through the diode. So let me draw the energy band diagram for a equilibrium tunnel diode. This is how the energy band diagram would look like for a equilibrium tunnel diode, where the overall band bending, if you see, would be equal to Q times the built-in potential of the tunnel diode. Tunnel diode symbol is like this. It almost looks like a normal p-n junction diode, except that it has these two lines. And the way I actually understand this figure is like this. So this symbol, if I flip it, it would look like this. And in general, if you are traveling in your vehicle through a tunnel, the tunnel entrance would look like this. So when electrons are going, basically the tunnel looks like this. Now let us understand how a tunnel diode works when we apply a potential difference across this diode. So to start with, let's say we apply a potential difference of 0. Then the energy band diagram would look exactly like the equilibrium energy band diagram. So the current flowing through the diode would be 0. So this is the first case. Now second, I'm going to apply some small forward bias to this tunnel diode. Let's say the voltage I'm applying is some V1. And we know when we didn't apply any potential difference across the diode, there is inbuilt electric field from n side to p side inside the depletion region. And because of the applied potential, V1, the electric field would be this way. Because these two electric fields are in opposite directions, the electric field in the depletion region would decrease. And the depletion width would also decrease. And as a result, even the barrier potential would decrease. So which means n side energy band should move up and p side energy band should move down so that the barrier potential would decrease. So let me draw the energy band diagram for this scenario. This is how the energy band diagram would look like, where the Fermi energy levels have split in this case, and the difference between these two Fermi energy levels would be equal to Q times V1, the potential that we applied. We have it multiplied with Q because the scale that we are looking at is actually in electron volts. That's why we have Q times the potential, which becomes electron volt. And the barrier potential would have reduced from QVBI to QVBI minus V1, the potential we applied. And now we can see on n side, below the Fermi energy level, we'll have a lot of electrons in the conduction band. And at the same time on p side, above Fermi energy level, we'll have a lot of holes. And because it is heavily doped, the depletion width would be really, really small. The depletion width typically in tunnel diodes would be in few angstroms or nanometers. So the depletion width is really very small. In general, the electrons are supposed to actually surmount the barrier in order to go to the other side. And similarly, even the holes, they should be surmounting this barrier and going to the other side. But in this case, we see electrons are at a particular energy, and there are a lot of empty states on the other side, separated by a very small distance, which means the barrier width is very small. In that case, electrons, instead of surmounting the barrier, they directly go this way. Even though there is barrier, electrons would not go surmounting the barrier. Instead, they go through the barrier when the width of the barrier is very small. And this phenomenon is called tunneling. And as now there are quite some electrons, let's say above this Fermi energy level of EFP, these many electrons can actually see these empty states on the other side can flow. So there are quite a bit of electrons which can flow. So there would be current flow in this case. So to represent the amount of current flowing, I've taken on x-axis the potential applied across the tunnel diode, and I on y-axis current flowing through the tunnel diode. So let me take V1 is somewhere here, and we have some finite current flowing through it. Let's call this as I1. And at the same time, let us put the value when V was the voltage applied across the tunnel diode was 0. In that case, the current flowing was 0. So we had this point. Now in next case, let us increase the forward bias that we applied from V1 to V2, let's say. Once we increase the potential difference across the tunnel diode from V1 to V2, then the barrier potential would decrease because Q times VBI minus V2. As V2 is higher than V1, then this quantity would decrease. As a result, EFN would have been a little higher compared to this case, and EFP would be slightly below compared to this case. And now we have a lot of empty states here and a lot of electrons here. Now if we observe, as the barrier potential has decreased, and if you see the overlap of how many electrons can actually see how many empty states, it has increased. So as a result, because of this tunneling phenomenon, you would see more electrons actually tunneling through this barrier width. So as a result, the amount of current that you would see would be higher compared to the V1 case. So let me plot it here. Now because of this applied V2 potential, there would be higher current flowing, let's say that is I2. And of course we know I2 would be higher than I1. To accommodate more space, I'm removing this part of the slide. Now let us apply more forward bias voltage to the tunnel diode. Let's say now we're applying V3, which is greater than V2. Now the energy band diagram would look like this, where EFN compared to V2 case would have gone up, and EFP compared to V2 case would have gone down. So as a result, we can see the number of electrons that can see this available states would basically decrease compared to V2 case. So the number of electrons which will go through the barrier into this side would decrease. As a result, the current that is flowing through the diode would decrease. So for V3, let's say V3 is here, the current would decrease. So somewhere here, let's say this is I3. Now let us increase the voltage across the tunnel diode even more. Let's say we're going to V4, where V4 is greater than V3. This is how the energy band diagram would look like in this case, where this band bending would be Q times VBI minus V4. And if you see here that there are no electrons which can actually see this holes on the p side, as a result, there won't be tunneling anymore. So which means the tunneling current would be 0. From now on, if we start increasing voltage beyond this point, current can flow through this p-n junction diode only by electrons surmounting this barrier, and similarly holes surmounting this barrier. This situation looks very similar to a normal conventional p-n junction diode, where the carriers are injected across the depletion region and they diffuse, recombine, and so on and so forth. So I can plot the IV characteristics like this. Let's say V4 is somewhere here, at which point the current would be very less. And if we start increasing the voltage beyond V4, basically there would be injection of carriers, electrons from n side to p side and holes from p side to n side. And that point onwards, the tunnel diode would behave like a normal conventional p-n junction diode, as the current would be increasing exponentially as we increase the voltage. So now let me draw the entire characteristics that we have seen for a tunnel diode in forward bias. So let me take all the points from different graphs that we have seen and This is the tunnel diode. Voltage across this is VD. And current flowing in this direction, let's say, is ID. Now, as the current is actually flowing in the direction of ID, we are taking a positive ID axis, and VD is positive. Then we have seen for different values of voltages, how does the current look? If you connect the dots for different values, the current would look like this. And we can basically understand this curve by taking sum of two curves, one telling the tunneling current, which dies down after some voltage, and the injection current, which would kick after the voltage like this. And if we add these two curves, we would get this curve. This indicating the tunneling current, and this indicating the normal conventional p-n junction current. If you observe the tunnel diode characteristics, there is a part of the characteristics which are very interesting, because in this region, as the voltage is increasing, the current is decreasing, which means the slope is basically negative. So the conductance, or the inverse of it, the resistance of tunnel diode in this region, which is specifically small signal resistance or conductance, is actually negative, which is very peculiar, and we haven't seen this kind of characteristics so far. We're going to give some names to certain points of this curve, and you see here the curve actually goes to a peak point. We're going to call it as V peak, VP, and the current that flows at that point is I peak, which is IP. And if you come to this point, it looks like a valley. So this point, we're going to call it as valley voltage, VV, and the current that flows at that voltage is IV. And we can say negative resistance or conductance of the tunnel diode is in the range when the diode voltage is in between VV and VP. Strictly speaking, at VV and VP, the slopes would be 0, which means there is actually no negative value as such. So that's why we are strictly writing it as this way. And of course, we haven't seen what if we apply reverse bias voltage to this tunnel diode. This is how the energy band diagram would look like if we reverse bias the tunnel diode. To understand how the energy band diagram came this way, I've kept here the equilibrium energy band diagram of the tunnel diode, where Fermi energy level is constant throughout the tunnel diode. Now, because of the reverse applied voltage, the electric field would be in this direction, and the internal electric field would also be in the same direction. So because of the reverse bias, the electric field inside the reverse biased tunnel diode, electric field would be high. When electric field is high, the barrier potential would also be high, which would be Q times VBI plus VR, the applied reverse voltage. And as this barrier potential is high, so the EFN should be moving down and EFP should be moving up. That's why we have this situation. Now if you see here, below EFP, there will be a lot of electrons present, and there will be a lot of empty states above EFN here. And even though we reverse biased, we have seen under equilibrium, the depletion width was like in angstroms or nanometers. So even if you reverse bias, the depletion width wouldn't have become so big. It would be still a small value. Now we have a lot of electrons here and a lot of empty states here. They're separated by a small barrier width. As a result, these electrons would tunnel through the barrier. And the number of electrons that can see the number of available states would keep increasing as we increase the reverse bias voltage, because this distance would be Q times VR. If we increase VR, the difference between EFP to EFN would increase, so more number of electrons would be able to see more vacant states. The number of electrons flowing would increase. As a result, if we keep on increasing reverse bias voltage, the current keeps on increasing. But the current would be flowing in this direction, which is in the opposite direction of the reference. So that's why we are plotting in minus I. And this reverse voltage applied would be related to VD as VD is equal to minus VR. That's why we draw in minus VD side. As we're increasing the reverse bias voltage, the current would increase drastically. So we can combine this with respect to this graph. So it becomes like this. So the complete characteristics of the tunnel diode would look like this. And coming to applications of tunnel diode, because of its small signal negative resistance, it can be used in high frequency oscillators. And in general, this tunnel diode responds very quickly. As a result, it is used in very high frequencies. So we can say high frequency oscillators. It so seems that tunnel diodes are very reliable. In the sense, the tunnel diode, which was actually first found in 1957, its characteristics even today looks almost the same. You can imagine a semiconductor device working so reliably with the same kind of characteristics for so long. So basically, they're very reliable. And that too, it seems they're very resistant to radiation as well.